Now we're ready to revisit our Taylor approximating polynomials. We've left them for the last several lessons while we've talked about all these convergence and divergence tests. Now we're going to bring them back in. We're actually going to talk about what they have to do with series and what their sums look like. And then in another couple of lessons, we'll tie them in with all of the tests that we learned. So what's the difference between a Taylor approximating polynomial and the Taylor series representation of a function? Well, remember, the approximating polynomial is a finite polynomial that approximates the output of the function for some x value very near that target point that it was built around. For us, that would be x equals a, right? And so this is a finite number of terms. It actually stops. They'll tell us how many terms they want us to generate, or they'll use some sort of notation that we're supposed to be familiar with that has to do with order and degree, or they'll tell us to generate the first, so many non-zero terms. But it is a finite polynomial that is just an approximation of the function. A Taylor series representation of the function, if it exists, and we'll know if it does, it is an exact representation of the function on some interval. That's not everywhere. That's not for all values of x, but on some interval, and that interval will, again, just like the polynomial approximations, be somewhere around that target point A that we built the polynomial around, but it has an infinite number of terms. It is a series. We are adding infinitely many terms together. These Taylor series are Taylor power series. These are Taylor power series. Why power? Because they are powers of x. There's 1, there's 2, all the way up to the power of n, and all powers as n tends toward infinity. So these are Taylor power series. The biggest difference between the polynomials and the series lies right here. Our finite number of terms gives us a good approximation of the function very near a. Our power series gives us the exact output of the function. I should say here, gives us the exact output of the function on some interval near a. The difference between a finite Taylor approximating polynomial and an infinite Taylor power series lies right here in this red box. You'll see that generating term for term, generating them is the same. We find the first how many ever derivatives, we put them over 2 factorial, over 3 factorial, and so on. We multiply them by this linear factor raised to the power of n for each term. We have, how many ever terms in the middle there that we need. Then we have our nth term. The AP calls this the general term. That's something we need to start calling it, the general term. But in the power series of infinitely many terms, there are infinitely many more terms past the general term. And that is evidenced by plus ... This is super, super, super important. Don't overlook that, because that is your only indication that you're dealing with a power series as opposed to an approximating polynomial. If they tell you to build the power series, I better see a plus ... at the end. If they tell you to build an approximating polynomial containing so many terms, I better not see a plus ... at the end. I know that's just a notation issue, but you know how I am about notation. So, the Maclaurin series, not surprisingly, is basically just a Maclaurin polynomial, which means it's centered at 0, with a plus ... on the end. That's it. Here's an exact example of a Maclaurin power series. It's Maclaurin because it's clearly centered at 0. And here are the first 4 non-zero terms. Or if we stopped right here, this would be P sub 3, right, of order 3. But since it has the plus dot 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 on it, we know that this is a Maclaurin power series. And it is a power series centered at x equals 0. So everything that we learned about our approximating polynomials carries straightforwardly right into our power series work. We're not going to have to learn any new notation or information besides that little piece of notation right there. And just as our Taylor approximating polynomials were centered at A, our Taylor power series are still going to be centered at A. You can clearly see all we have to do is generate how many ever terms they tell us to, the first several terms in our approximating polynomial, and then just put a plus dot 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 at the end. Here's an exact example of one. This one is an alternating Taylor power series centered at x equal -1. So in this case, A is -1. We generate the first how many ever terms that they tell us to. That should be a plus there. And then we put a plus dot 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 at the end. That is the difference between an approximating polynomial and a series when it comes to power series. Why? Because they are power terms. When we first started learning derivatives, we had the derivative rules that we learned, where the power rule was when x was raised to a power. So power means it involves a variable, and it involves a variable raised to a power. That's why it's called a power series, because it involves power terms. And now we have series that involve variables. Now, we had n before in all of our series. N still shows up here. N still plays the same role that it did in our other series. But we never had x involved before. So now we're going to have to see what all those tests look like for these series that involve not only just n, but x as well. So let's generate some power series. Find the Taylor series of f that is based at x equal pi over 4 for f of x equals sine of x. Now, on the AP test, you won't have to wonder how many terms you should show. You won't have to wonder if you need to show the general term. They'll tell you. This doesn't tell you. This just says generate the power series. So I want you to, while we're doing this, we're going to show at least the first 4 non-zero terms, because I see that a lot on the test. Show the first 4 non-zero terms. Okay, we see that a lot on the test. So that's what we're going to do when we do these examples. So all we have to do is exactly what we did to generate our approximating polynomials. We're going to need f prime of x. We're going to need f double prime of x. We're going to need f triple prime of x. That is the very least that we're going to need to show the first 4 non-zero terms. Because remember, we have f of a plus f prime of a times x minus a. That's 2 terms. Plus f double prime at a over 2 factorial times x minus a squared. There's the 3rd term. And f triple prime at a over 3 factorial times x minus a cubed, and then plus dot 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 if we're making a series instead of an approximating polynomial. That's the very least we're going to need for the first 4 non-zero terms. If any of these values are 0, then we're going to have to add another term. We're going to have to generate another term. All right, so let's do this. If f of x is sine of x, f prime of x is cosine of x, f double prime of x is negative sine of x, f triple prime of x is negative cosine of x. Now, again, what we need is we need those evaluated at A. Now, just like The AP does. This says based at x equal pi over 4. It might say about x equal pi over 4. On the test, they're not going to call that center point A like we've been calling it for our approximating polynomials. And that's just fine. X equal pi over 4 is the center point around which these series are based. So we need f of pi over 4. We're going to need f prime of pi over 4. We're going to need f double prime of pi over 4. And we're going to need f triple prime of pi over 4. So f of pi over 4 is the sine of pi over 4. That's root 2 over 2. This is the cosine of pi over 4. That's root 2 over 2. This is the negative sine of pi over 4. That's negative root 2 over 2. And this is the negative cosine of pi over 4. Again, negative root 2 over 2. So the power series, which is just p of x, not p sub n of x, is f of pi over 4 plus f prime of pi over 4 times x minus that center point around which we're building, or that center point at which we're based. That's our point of tangency. Plus, this is the third term of the non-zero terms, because none of those coefficients went to 0, so we don't have to find any more derivatives. And so the next one is negative root 2 over 2 all over 2 factorial. Remember, I have to remember to bring the factorials to the party. I have to remember to bring the linear factors to the party. And the last term is negative root 2 over 2 over 3 factorial times x minus pi over 4 cubed. This is a power series, so I can't forget the plus dot dot dot, because without that, I have built an approximating polynomial. That is not what they asked for. They asked for the Taylor series for the function centered around pi over 4 or based at x equal pi over 4. So it's identical to the work that we did before when we built those approximating polynomials. The only difference is we've got to remember to put plus dot 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 at the end. Let's build another one. Here's one at pi over 4. Again, we're going to show the first 4 non-zero terms. Lots of times they'll ask for the general term as well, but I'm going to save that work for later on. We'll get started on this example. I don't know if we'll finish it or not, but here's f of x. We need f prime of x. That's negative sine of 2x times 2. We'll need, for sure, f double prime of x. That is negative 2 times the cosine of 2x times 2. We'll need f triple prime of x. That's negative 4 times a negative sine of 2x times 2. We could clean these up if we wanted to. That's negative 2 sine of 2x. This is negative 4 cosine of 4x. This is positive 8 sine, not 4x, that's 2x, of 2x. Sorry, going a little fast trying to get through here. Then we'll need f of pi over 4, f prime of pi over 4, f double prime of pi over 4, f triple prime of pi over 4. That'll be a good place to stop. We'll pick this example up in the next video.